Good morning, everyone. Thank you so much for joining us for another technical committee-induced seismicity webinar. Today we have Men-Andrin, Meier, and Valentin Gischig from ETH Zurich. First of all, uh, sorry, let's go back to the first slide. So we have this is 63rd ARMA Technical Committee Induced Seismicity monthly webinar, and on behalf of the webinar committee, welcome to this webinar. Today we have Men-Andrin, Meier, and Valentin Gischig from ETH Zurich, and the title of the talk is Activating Natural Faults and Fractures at the Bedretto Lab. In the following months, we have two scheduled webinars by Kyung Joy Im at Caltech on January 9, 2026, and Brett Carpenter from University of Oklahoma on February 6, 2026. Before getting started with the presentation, I would like to have some housekeeping items. Please feel free to share the webinar invite with the interested colleagues. Also, we have this option to add them to the invitation list if they are interested in receiving the webinar invites for the following months. Please submit your questions during or after the talk in the chat button at the bottom of the Zoom meeting window, and please send these questions to everyone for us to be able to use better to summarize the repetitive questions or have better use of time at the end of the presentation. This specific meeting is recorded and it will be uploaded in our YouTube channel. Please subscribe to that channel for future notifications of the uploads. And before getting started, I would like to read some lines about the presenters. Men-Andrin Meier is a lecturer at the Department of Earth and Planetary Sciences at ETH Zurich. He is the lead scientific coordinator for the ERC project, Fault Activation and Earthquake Rupture at the Bedretto Underground Laboratory. His research focuses on fundamental scientific questions in earthquake rupture physics, seismic risk mitigation, and the application of machine learning techniques for monitoring seismogenic processes. And Valentin Gischig is a scientific collaborator at the Swiss Seismological Service at ETH Zurich. His research involves geomechanical processes linked to natural hazards, enhanced geothermal systems, and clay shales. He has contributed to subsurface monitoring for engineering stimulation patterns in fractured reservoirs, including work at the Bedretto Underground Laboratory for Geophysics and Geoenergies. Without further delay, let's invite the presenters to take over the stage and present for us. Thank you so much for presenting in advance.
Thanks for the introduction.
Thank you very much for the introduction and for the invitation. Excited to be able to show our work at the Bedretto Lab here in this format. So we will be talking about activating natural faults and fractures at the Bedretto Lab in southern Switzerland. And the work that we present is not just from Valentin and myself, but from a large team of Bedretto Lab scientists. We're about 50 scientists and then a lot of engineers and technicians and admin people. And so it's a very large project that we work for. Our key motivation is that many first-order processes in earthquake mechanics are poorly understood for two main reasons. One is because they are very complex with processes at various length and time scales and also interacting. And also they are generally hard to observe. So often we try to understand what happened in the subsurface, mostly with rather long distance observations, for example, from surface arrays. And so this really hinders the development of more efficient seismic risk mitigation strategies. And as I'm sure everybody in this audience knows, that this is also a major obstacle for a lot of underground projects, which have a seismogenic risk component, for example, in deep geothermal energy. So in earthquake mechanics, we're often observation limited. So if we think of a rupture that is, barreling along a fault, there's a lot of processes that happen at all sorts of scales, including very small scales, that we know are very relevant for rupture dynamics, but that are usually much too small to constrain. So, there's rupture tip processes and faults cracking and melting in a lot of places, but often they don't melt because there's dramatic weakening. What are the weakening mechanisms? What do the fluids do? There's a lot of these processes that we know have first order effects on how earthquakes and faults behave, but we can usually only study them in rock mechanics laboratories or in numerical simulations. And now, wouldn't it be incredibly interesting if we were able to just drill a hole through a fault and cement in, for example, some 5% optic sensing cables, and make a rupture through these cables so that we could measure some of these processes in situ as they occur in real earthquakes rather than in rock mechanics lab experiments. And this is essentially what we're trying to do in what we call the FEAR project. So it's the Fault Activation and Earthquake Rupture Project, where we try and we have identified and characterized a target fault zone in the Bedretto Lab. Now we're in the process of densely instrumenting it. And then we want to make it move. Make it move, we mean to make magnitude 1 scale ruptures. So ruptures on with rupture dimensions of tens of meters and maybe a couple of millimeters of slip, with the idea that then if we have these in situ on-fault observations and from very short distance observations, we can hopefully elucidate a lot of the rupture physics that usually is below the sensitivity and the resolution of more standard observatories. I mean, if we could really do that, we believe that we could potentially advance our understanding of the earthquake seismic cycle from pre-seismic strain focusing, post-seismic effects. How does a dynamic rupture interact with the fault structure on which it occurs? How does that affect high-frequency seismic radiation, all the way to rupture arrest, post-seismic phenomena, etc. And so today we want to provide a bit of an overview of where we stand in this process of activating the natural faults and fractures at the Bedretto Lab. We start with a brief overview of the Bedretto Lab, then a set of experiments that we call the M0 experiments at the geothermal test bed, which is a part of the Bedretto Lab. And then the second half will be about the FEAR project, where we built a new earthquake physics test bed. We're in the process of building this right now. We're running an intense characterization campaign, and we have some very short segments on first experiments and observations. So let's start with the Bedretto Lab. The Bedretto Lab is in the middle of the European Alps. So this is a map of Switzerland. Here's the Alps, and Bedretto Lab is here in the middle of it. For reference, this is Zurich and Basel, St. Gallen, that probably many of you know is around here. And so if we zoom in a little bit, we see this Bedretto Lab over here is the Aletsch Glacier, which is the largest glacier in the Alps. We have some glaciers north of the Bedretto Lab. The Bedretto Lab is under this ridge of the Pizzo Rotondo. It's a 5-kilometer long tunnel that was built in the 70s. It was once called the most useless tunnel ever built in Switzerland, until ETH repurposed it for this deep underground laboratory. And this area itself used to be intensely glaciated, so the maximum extent of the glaciers of the last ice age covered also the southern flanks of these mountains. All that's left now is the smaller glaciers on the northern side of the Pizzo Rotondo. And what's left here on the southern side, this is the Pizzo Rotondo, are these massive moraine and debris fields above the lab. And so the Bedretto Lab is almost exactly under this ridge of the beautiful Pizzo Rotondo. And so because we have this tunnel at depth, we have access to some natural faults and fractures that we can play with and study as geophysicists and geochemists. So this was a brief overview of the Bedretto Lab. I should maybe say, so there's 2 test beds. If we go in for 2 kilometers, there's what we call the geothermal test bed. This has been in operation since 2021. We have several several 100-meter long boreholes, including 2 stimulation boreholes with a multi-package system installed. And now we're in the process of building a couple 100 meters deeper in the tunnel, what we call the earthquake physics test bed around the target fault zone of the FEAR project, of which I will tell more in a minute. But first, I'll pass on the word to Valentin Gischig, who will present on the M0 experiments at the geothermal test bed, so the first test bed.
Yes, thanks. I hope you can hear me well. So yeah, Men-Andrin showed the Bedretto Lab highlighted that we're constructing this so-called earthquake physics test bed. What we've done in the last, let's say, 5 years, we constructed a geothermal test bed and tested hydraulic stimulation programs, strategies, and reservoir borehole completion strategies in this so-called geothermal test bed. And while preparing for the earthquake physics test bed, we wanted to make use of this test bed to try a couple of things. And specifically, we conducted one major hydraulic stimulation that we call the M0 experiments. And the goal of this M0 experiments was, as the name says, to induce a magnitude 0 earthquake. In the earthquake physics test bed, it's going to be a magnitude 1 earthquake. So it's preparatory in this sense to slowly step up. It was also a goal to actually test different preconditioning injections, different preconditioning concept to enhance seismicity. So this test bed has been constructed to investigate how we can reduce induced seismicity for geothermics, but it's just as useful to actually see how we can enhance seismicity. And I'm going to tell in a minute why we wanted to enhance seismicity. It's a great opportunity to use this test, but also because there's already a 3D sensor array installed. We had made a new remote control pump system, which is a relevant ingredient to this experiment. It also allowed us to do experiments while not being in the tunnel for safety reasons. This is also good preparation for the magnitude 1 Earth experiments. And yeah, so with this, we can already try and investigate fault processes close to the fault, but not yet on the fault. So if you can go one slide further, man. So here's the what I mean with the dense instruments here. There's the experiment niche. You can see all the boreholes that are drilled in an inclined angle from this experiment niche. The longest one, called SD1, is 400 meters long. And you can see these different gray dashes. These are different intervals that are separated from each other by a multi-packer system. Exactly. So if you point out the red dash, that's basically our target interval. This is the interval 11 that I'm going to talk more about. Around, you can see several boreholes. There are multi-packer system just for monitoring purposes. All the circles, there are FPG sensors. So these are sensors that pick up linear strain. Most of these boreholes are also equipped with fiber optics to pick up distributed strain and also the distributed temperature. And to the top right, you can see that there's a lot of seismic sensors there as well. Acoustic emission sensors, accelerometers, geophones. Not all of them are still alive, but still a high number so that we can get a high resolution seismicity cloud. If you move on to the next slide. So yeah, this is the seismicity cloud of all the past experiments that have been performed in this volume. So we know quite well what's going to happen if you inject in this particular rock mass. And if you click further, now also in this interval 11 that we targeted, there has been a number of hydraulic stimulation in the past. You can see them here, the pressure curve and the seismicity distribution on the vertical axis, on just the set component of the seismicity. And you can see that it's always been a volume between 1 and 10 cubic meters on the order of magnitude. If you continue 2 clicks, you can then see these so-called M0A and M0B, the M0 experiment sequences. And I'm going to talk a little bit more about them in the next slide. So if you continue now. So we do know a lot about this, the seismogenic response of this volume. And we calculated and found, we estimated that we need a lot of volume to actually induce a magnitude 0 event. And that's going to be the same in the earthquake physics testbed. So it would be useful to find a way to enhance seismicity and to, well, even to control sort of the magnitude of the seismicity. So we tried a preconditioning protocol, and you can see the experiment sequence below. If you focus on the red areas, in the first experiment sequence, we tried preconditioning, and preconditioning, with preconditioning, we mean that we pressurize an extensive volume of the rock mass so that it's getting close to failure, but not yet failed. So it's just below the checking pressure or the seismic reactivation pressure. And then if we've done this for a large volume, then we ramp up the pressure to a larger magnitude, to 20 megapascal in our case, to actually kickstart seismicity. There are a couple of additional experiments I'm going to highlight later, but in the M0B experiment, like half a year or a couple of months later, we've repeated the same experiment without preconditioning. So we just did an extensive hydraulic stimulation at 20 megapascal without preconditioning. So we also wanted to keep track of the hydromechanical properties, checking pressure, injectivity, but also the seismic reactivation pressure over the course of these experiments. And for this, we've done these yellow tests, which are called step pressure tests, or SPT test in short. And the good thing about this, because of the remote controlled or controlled pump circuit system, we can do them in a really repeatable manner. So that's the experiment sequence, and then I like to jump to the couple of results already. So here you can see this main stimulation of M0A, so the preconditioning plus the main stimulation on the left, and to the right M0B, where we just did a hydraulic stimulation without preconditioning, and you can see the differences. And there has been some sparse seismicity already during preconditioning during this M0A experiment. Then we started the main stimulation, and after 16 hours, we were really pleased because we induced a magnitude 0 event. Well, it was a local magnitude 0 earthquake. And we were happy, said we have reached our experiment goals. We shut in the well and we bleed off the well, also for safety reasons. Later, it turned out that the moment magnitude NW is minus 0.5, so still considerable. And what is noteworthy is that it really is a step out event, in that it's one magnitude scale larger than the second largest events before it. What you see, if you on the zoom in, the figure H here, is that this main shock, what we call it, is triggered a lot of aftershocks, and Men-Andrin is going to highlight this more after. What you see, a couple of minutes later, we shut in and we bleed off the well, and the bleed off, not the shut in, induced an additional burst of seismicity. So now if we compare the M0B experiment, there has been a higher flow rate during this experiment at exactly 20 megapascal. There has been more seismicity, and the seismic events were larger, but we didn't have such a step out event. There were, in fact, two events which also triggered some aftershocks, but the magnitude 0.5, minus 0.5 earthquake was really significant and significantly stronger than all the other events. So if you continue on the next slide, Man is going to talk more about the seismicity structure of this sequence here. Just one thing that I'd like to highlight. If you look at the seismicity migration pattern of the M0 experiment, just the 25 cubic meters injected during the main stimulation, we can not see too much of a migration front. Whereas if we look at the equivalent volume injected at the beginning of the M0B experiment, the first 25 cubic meters injected, we can see something like a seismicity migration front, as if it looks, one would, if we stimulate a fracture network for the first time, this is what we would expect, that we have an outward propagation of seismicity. Whereas what we had on the left, basically in the earlier experiment, is somewhat unexpected. It's much more diffuse seismicity occurrence. So if you continue to the next slide, here you can see the number of events normalized per injected volume. The number of events was much higher during the M0B experiment. P-value was a little lower, but somewhat comparable. And what I'd like to draw your attention to is the bottom figure, which actually shows the number of events per cubic meter for all the old experiments that happened already in this interval. There were high numbers of 100 to 1000 events per cubic meter, and this slowly then decayed. It's kind of expected. With time or with repeated experiments, you kind of wear out the seismic response of a reservoir. But then these SPT experiments started, the M0A and M0B experiments were performed, and it almost looked like this seismogenic response recovered again. And also what I highlighted for the migration pattern, it looks like the seismogenic response in terms of what we expect in terms of the seismicity migration looks like we sort of have reset the fracture networks. And we have sort of recovered the seismogenic response again after M0A. So what has happened here? If you continue to the next slide. So let us focus quickly on this SPT test. I already mentioned that we had the capabilities to do them in a very repeatable manner. You can see on top, it's pressure-controlled experiments. These are 7 experiments, pressure curves on top of each other. Below is the injection rate that evolves during this experiment, and below the cumulative seismic events. And you can see that the seismic response sort of looks quite different. So if you click one more, this kind of summarizes the observables that it can be derived from this step pressure tests. We can look at injectivity, how it evolves, and we can look at the checking pressure. We can see, for instance, the checking pressure has increased by more than 1 megapascal after the M0A experiment, not so much after the M0B experiment. But we can also see, again, the number of seismic events. There was a drop from after the first SPT test, after a production test. Then between the M0A and M0B experiments, the seismicity kind of came back to its original level, so to say, and even beyond it. And also the level above which the seismicity is induced, the sort of seismic reactivation pressure reduced. So it became easier to produce seismicity in this reservoir after M0B. What I also put here into this subfigure D, if you click one more time, it kind of highlights this part here, the blue squares here. This is a pressure reading from a sort of far away pressure monitoring interval, 100 meters away from the action. And this undergoes also an evolution, and looks like this evolution of background pressure, ambient pressure, follows more or less the seismogenic response proxy of this SPT test, derived from this SPT test. So if you continue to the next slide, here's what I mean. The pink dashes there, the timing of this SPT tests, and below are long-term pressure evolution of this reservoir. We can see clear seasonal cycles. The pressure increases at snow melt, and it decreases in winter. And it looks like these SPT tests have been performed in quite different times or different conditions when it comes to ambient pressure conditions. And we may wonder if this ambient pressure level has actually dictated what the seismogenic response has been and actually helped to reset the seismogenic response of the reservoir. If you continue one more slide. So here's another interesting feature about this main shock, about this magnitude 0.5 earthquake. What we found here, if you look at the pink dashed line, and I mislabeled the earthquake with minus 0.4, it's actually 0.5. What we see, the flow rate dropped after this main shock. And below you can see the pressure monitored in this very interval downhole. We can see that the pressure increased right after this main shock. And given that we wanted the pump circuit system wants the pressure to stay at exactly 20 megapascal, it had to fight against this pressure increase and reacted with a flow drop. But long story short, basically there was more resistant to flow all of the sudden. We can also see pressure evolution from a couple of other pressure monitoring intervals where we see a change in the curve right at the occurrence of this main shock. And in the right panels, you can also see strain data from FPG sensors, so linear strain. And we can see we have picked up a small but clear co-seismic strain. And this is about 0.1, 0.3 microstrain. So this main shock has evidently made changes in the reservoir that we can pick up from different observables, not just from seismometers. And if you continue to the next slide, perhaps, kind of confirms what we observe in this pressure curves and in the flow rate that after the M0 experiment, the transmissivity changed. You can see here the evolution of transmissivity that comes from a range of hydro tests that was conducted in this interval over the last almost 4 years. The transmissivity increased with each of the small stimulations. And then after the M0A experiment, it dropped to about half of the level. And it increased again after the M0B experiment. But this sort of confirms that these stress interactions and this hydromechanical changes kind of affected the transmissivity. Next slide. We also try to know the focal mechanism of this main shock, and we try to predict the different the strain along these different boreholes and the volumetric stress changes in the injection interval, and we can kind of confirm our observables. So here the prediction on the top right, the prediction of the deformation and the actual observations don't match exactly, but reasonably well. And we find that we're on the range of some 10 kilopascals. So 10 kilopascal stress change, I guess it's not enough to actually change the seismogenic response. So this is perhaps not sufficient to explain why the seismogenic response of M0A and M0B has been different. But considering that there's not just the main shock, there's a whole seismicity cloud, there's also aseismic processes, perhaps all this together help to change the stress conditions, the hydromechanical conditions of the reservoir such that the M0B experiment was so different. So if you continue to the next slide, why did I conduct this discussion on what else could produce the M0B response? Basically, it's the same if we test different injection protocols and to enhance or to reduce seismicity. We're also always facing the same issue. We come into an interval, into rock mass, which has a history. It's also subject to seasonal changes. It is subject to changes when we stimulate it. And actually, decide if the preconditioning now has worked or not is difficult. We have to also consider the history of the interval. We have to consider the ambient pressure changes. We also have to consider the seismicity of the first experiment versus the second one. But yeah, we may also argue that there's hints that this preconditioning has worked because after all, we have produced this step out event. And yeah, I like to pass on to Men-Andrin now to discuss the seismicity patterns a bit more in detail.
Thank you, Valentin. So going back to this figure that you already showed, one of the things that is very exciting from a seismology and geology perspective of these data sets is that we have, with these extensive 3D arrays, quite impressive, I would say, not just sensitivity, but also resolution in terms of the spatial hypercenter location, accuracy, and precision. So if we draw a vertical profile through the seismicity cloud, we see the individual structures in many cases very sharp. So we can see, planar features. Then here, this is actually along a borehole, and then a step over to new structures. I can try and actually animate this outside the presentation, assuming you can see this. The largest quake that we observed, this main shock, the minus 0.5 event, occurred up here, right at this step over to new structure. If we just slide through the volume and look at these profiles in different places, we just see an incredible structural inventory that is almost detailed enough to basically do structural geology based on seismicity data. And so if we look at this, the M0A and B events in some more detail structurally, then we see that we have this planar structure. Then there's a bit of a gap here, and then the next structure is active further up after a step over. And these blue dots are actually from the M0B experiment. So this wasn't active, or not much active, in the M0A, and only after, only in the second experiment did we substantially activate this structure. And if we zoom into the main shock here, this is taken from the focal mechanism, and assuming a stress drop of 10 megapascal, and we see this rupture plane that, or presumed or approximated rupture plane that would fill this little gap here that hadn't been very active in any of the previous experiments. And if we look laterally, so if we, instead of slicing the seismicity vertically, we slice it horizontally, we see that the rupture also happened at a complexity of this of the structural inventory laterally. So this is the main shock, the same plane that we computed with an assumed stress drop and the focal mechanism, and we see that it happened here in this little kink. If we instead take on an in-plane perspective, and these plots are a little busy, but we see that this is the circle of some estimated rupture area from some fitting a broom model to the seismic data. We see that that's sort of the gap that was relatively quiet in any of the previous experiments. There was 2 hours previous to the main shock, there was a minus 1.8 shock that was very close in space. You see also this one yellow dot. So this is a place where the event maybe has tried to nucleate. This was in 2022, so a long time before, but it wasn't ready. We didn't force it enough, and it didn't go then, but later it erupted. I think this may speak to sort of the dynamic stability of faults, like we also see in natural fault systems, for example, in Amatrice, where we had in the central Apennines in Italy, where we had, the Amatrice rupture that was magnitude 6 and really shook the area. And then some 2 or 3 months later, there was the Norcia 6.5 earthquake that was, at the time of the first main shock, was almost, but not quite ready to go. If we look at, again, a horizontal slide, we also see that we find a lot of correspondence between what we see in the seismicity and the structural inventory that Alberto Ceccato, one of our geologists, mapped at the surface. So this is a geologic map and interpretation with these fault lines, and we see very similar types of structures with these kinks and orientations down, over a kilometer deeper under the pizzo rotondo. And so, as a little summary from the seismology perspective, so this minus 0.5 main shock actually occurred at the sharp upper edge of the seismicity we had in the experiment and just below this step over structure. If we look at magnitude frequency statistics, we actually see that this upper edge of seismicity is a very pronounced p-value anomaly. I apologize for having omitted the color scale, but the red colors are p-values, Gutenberg-Richter p-values in the order of minus 1.1, and the blue values are on the order of 1.4. So there's substantially lower p-values up here and correspondingly a larger number of relatively large magnitude events. And the main shock happened really in the middle, in the very heart of this anomaly. We had this one large foreshocks 2 hours prior, but we did not see a seismicity rate increase before the main shock. So this is the seismicity rate and number of events per 5 minutes throughout these 16 or so hours of injection. We see we have relatively constant rate, drops a bit halfway through the experiment, and then without any rate increase, there was just this jump that is actually the aftershock sequence of this main shock. And Valentin has already alluded to this. The main shock appears as a step function at the nearest strain sensor. So we have these FBG axial strain sensors in the cemented boreholes. This is one recording from one of these sensors that's relatively close, and we see this is a very strong poroelastic response all the way to here, and this is the jump that is caused by the main shock shear deformation. And so we can actually also compute the focal mechanism, invert these permanent strain signals, and we get a very good correspondence between the seismic and the strain focal mechanism. If we zoom into here, we see it's really a step function with the temporal resolution that we have. We hope that we would see maybe an aseismic nucleation, but either this didn't happen, or meaning that the event would have started abruptly, or we just, even with 20 meters, we're still not quite close to this event that is only a couple meters long. This event started an intense aftershock sequence, as already shown by Valentin. This is a 3-second seismogram in one of our acoustic emission sensors. You see here that this is the main shock, and then we literally have hundreds of aftershocks in a very short time period. So in these 3 seconds, and we count about 100 events, but only some of them are picked up by our standard SeisComp monitoring system. All the double red triangles are picks from our routine automated monitoring system. And PhD student Lu Tian is now working on a machine learning model, UNet phase detector that does a much better job of picking up these subtle signals, and is working on compiling a deep learning based seismicity catalog. So this was the M0 experiment at the geothermal testbed. So in this first lab that we've already been operating since 2021. And now we would like to move on to the fault activation and the earthquake rupture project, and starting with the process of building this earthquake physics testbed. So we go from the geothermal testbed that we now just talked about in some detail. We go about half a kilometer deeper into the Bedretto tunnel, and where we are in the process of building this earthquake physics testbed, where we want to make the magnitude 1 quakes with direct in situ on-fault observation. And so what is a magnitude 1 quake? If we assume some, reasonably or reasonable parameters for stress drop and rupture speed, then we would have a rupture of about maybe 50 meters length, so in a couple of millimeter slip, and rupture durations of 0.01 seconds, a fraction of a second, and it gives you an idea of sort of the time resolution that we need to have, for example, with our seismic monitoring in order to capture rupture processes that are so short-lived. And so, for example, the acoustic emission sensors, we sample at 200,000 samples per second. We haven't managed 1.0 yet. We're still in preparation for this. The magnitude 0 quake would be sort of a bit smaller than that, and a couple of meters across. And this is also consistent with what we find from this aftershock cloud that I showed earlier in the vertical profiles. So in order to build this earthquakes physics testbed, we had to identify a target fault zone. This is described in this Aftergood-Sabancic et al. Paper, we found a very good candidate fault zone at about 2.5 kilometers into the Bedretto tunnel. It cuts the Bedretto tunnel almost perpendicularly and has a relatively steep dip. It's about 2 meters wide. It's structurally immature, and some of these strands have gouge layers that are not continuous across all the interfaces, but they are present in many places and up to several millimeters thick. Despite this, when we showed this to some of our favorite geologists that are not in our project, some of them were quite skeptical and sort of said, yeah, this is quite cute. This is a crack in the wall, and it will stop after a couple meters. And so we were quite concerned, and we drilled these prospection boreholes to sample the same structure at larger distances. And then we were very excited when at some 38 meters into the borehole, we actually found it again in acoustic televiewer logs, and also we call these prospection boreholes that we drilled. And you see sort of in this longer borehole that we see the sort of Tonda granite that we're in is relatively intact. There's some pronounced structures in some places, but they're relatively well-defined structures that we can use to try and activate on purpose. And so because we had found this target fault zone, we thought we can move ahead and try and build this earthquake physics testbed around it. And so this is a schematic view of sort of the idea that we had when we started doing it. This is the Bedretto tunnel with the red floor, and now we actually excavated this fault parallel ferrite tunnel. It's about 110 meters long, and it runs parallel to this fault zone at the distance of about 40 meters laterally. And so what the goal is to produce a sequence of ruptures on the order of magnitude 1 on this target fault zone with dense instrumentation around, but also on the fault. So we try to drill through the fault and actually cement in, for example, fiber optics cables. This is the plan of the monitoring system that we're in the process of building. So the red ones here are these prospection boreholes, and this one as well. So it goes through the fault zone actually. There's downgoing, upgoing boreholes in all directions, and they carry these strain sensors, seismic sensors, pressure gauges, and a lot of other equipment. But before we could do this, we had to build the tunnel. So we started excavating the tunnel, which of course was a major mission. First, we had to make the space for the tunnel construction in the first place. This is after some time of tunneling. It was a very intense construction process, but went very well. And so this is now the complete tunnel. This is the end niche here after 110 meters. In the middle, we have this trench for cementing in fiber optics cables with DAS, DTS, and DSS. This is the FEAR science team at our annual meeting in Airolo. There's Domenico Cialdini, I think Stefan Mimmer somewhere in the background, and Massimo Cocco and Florian Amman are also somewhere, Marijn Hertrich in the middle, the head of the lab. And I want to point out that it's quite incredible that after 20 iPhone generations and an artificial intelligence resolution, we still get about 5 pixels per face. But I think you can see that we're smiling. So we're quite happy with how this has turned out. This is a picture actually from 2 days ago. So we're at the moment doing active seismics in some of these boreholes. So this is a very ongoing instrumentation campaign. But it doesn't actually look all that different from what we had planned. And so the timeline is that we have done these experiments, the M0 experiments in 2024 at the geothermal test bed, which again is a bit less deep in the Bedretto tunnel. Now we did, and then we actually did FEAR 1, which was sort of before we had the tunnel. We already injected over 1,000 cubic meter of water on this side to try and activate the fault aseismically before we're fully ready. Then we did tunneling until June of this year. And then we drilled a lot of boreholes, and now we're in the process of instrumenting this, and we're planning these experiments in 26 and 27. There were a lot of challenges along the way in these sort of talks. We often just present the things that work really well, but it wasn't exactly a walk in the park. It still isn't. We found in the FEAR 1 experiment that it's that we also activated other structures that were other than the main fault, and now we're thinking how can we best avoid to activate structures that we didn't that we're not targeting, because of course our monitoring system is quite fixed, and so the worry is that if we um, activate other structures, then we'd have to be quite lucky to get the same kind of monitoring sensitivity and resolution. It's difficult to place sensors close enough to processes. So for example, if we want to measure coseismic strain, we have to be really close to see through the very strong pore-elastic signals that we're getting. Of course, there's a lot of budget and time constraints. We are actually a bit late because of various delays that are common, I guess, in such projects. Every borehole that we drill is basically a perturbation of the hydraulic system that we want to minimize. And there's always the risk of stuck probes. We have plenty of that, faulty cementation, etc. So this, just to say that it's not just an easy process, like we sometimes makes it seem in these sort of presentations. This is a GPR image. So once we had the FEAR tunnel here, we could do tunnel wall GPR, and we actually see the fault zone very nicely. Here is where it outcrops at the Bedretto tunnel. There's other prominent structures, but the target fault zone is visible to at least 80 meters away from the tunnel. So big enough for these magnitude 1 ruptures, presumably. I'm rushing through this a bit because I think I'm getting quite late. We're putting all sorts of different types of instrumentation on and around the fault zone. Our paper on this should be coming out relatively soon. So if you're interested, you can read it up there. And if we have enough time, Valentin, maybe you can briefly say something about the characterization campaign, because that's another thing that the Bedretto Lab facilitates because of this direct access.
Yeah, perhaps just a couple of short things. Men-Andrin already mentioned the GPR measurements. We, of course, do logging as well in all the boreholes as they are drilled. If you click a bit more, you can see that these acoustic telemeter logs, they align very well with the prediction of the GPR data. And with the core, with all the geophysics that we put in, we will be able to construct a 3D geological model. So of course, to avoid some of the risks, but also to understand the data later, this is a key ingredient, the 3D geological model. But we also need a bit more. A main driver for earthquakes is stresses. So we should understand the stress field quite well. What you see here is a regional or a tunnel scale stress model. It's a model that succeeded in reproducing the stress measurements that were done a couple of years ago in the geothermal test bed, so 500 meters away. They predict normal faulting, although pretty close to strike slip faulting, and the models then predict predominant normal faulting in the region where we want to conduct our experiments in this FEAR volume. Now, sure, we should confirm this. We should also understand the stress heterogeneity around this fault. It will tell us something about its properties as well, and about the processes later. And if you continue to the next slide. So we performed a number of mini frag tests. You can see here in red the target fault. You can see all the green dots, which are mini frag locations in these different boreholes. You can also see red dots, and these are dots where the mini frag did not succeed because we couldn't reach the breakdown pressure with the pump equipment. So basically, the breakdown pressure must have been beyond more than 40 megapascals. So that alone tells us something. And it tells us that something is changing as we going here on the left from the target fault. And if you go then to the next slide, what we found is here, these are pretty preliminary results. This is the work of our PhD student, Barnabas Köver, who is in the process of analyzing all these tests. What you can see here, these numbers, is the sigma 3 magnitude, which is easy to derive. We see a clear difference between what we observe, the right side and the left side of the target fold. And specifically, the sigma 3 magnitude changes a fair bit. It's about 19 to 25 megapascal on the left side. It's more 15 to 18 megapascal on the right side. And it also changes as we go towards the fold. And some preliminary analysis on the fracture orientation that we analyzed, we think that it's normal folding dominated to the right, as predicted from the old measurements and from the model, but to the left, it's actually strike slip. And yeah, we need to understand this, but I'm sure this is highly relevant for the outcomes of the results as well. We're also doing hydro testing, of course, and while doing hydro testing, we find surprises. For instance, we see there's a flow coming from different fractures, not just this target fold as anticipated. It's relevant for understanding the experiments, the reaction of the fold, but also for the design. It's difficult to cement in instruments into a fold that is into a borehole that is actively flowing. It has time implication, it has financial implications. So this is all part of the process. So back to you, Men-Andrin.
Good. And so maybe I'll skip over this last bit of the first experiment. So I just briefly mentioned that we already injected a substantial amount of water in November, December on the right side before we had the tunnel, over 1,000 cubic meter. And this is an example of the wide ranges of data that we have. And this is our Grafana cockpit that we use to steer these experiments. This is us because of the remote control system. We can actually conveniently and safely do this from the control room in Zurich. And now what we're doing is basically we're inverting all these different types of data, for example, for shear dislocations model that would explain all the data types. And so this is it. This is our efforts of activating natural faults and fractures at the Bedretto Lab. And the Bedretto Lab offers this direct access to natural fault zones at depth. The FEAR project is our somewhat bold attempt to observe and study faulting processes in situ and simultaneously cover all the major observables, such as strain, slow and fast fault deformation, temperature, pressure, and more. And these are processes that we can usually study only in lab experiments and in numerical simulations for ongoing ruptures. Our goal is to improve our understanding of earthquake ruptures and the risk across the seismic cycle. And with this, we would like to thank you for your attention, and we'd be very happy to answer all your questions if we can.
Awesome. Thank you so much, Men-Andrin. Thank you so much, Valentin. It was very interesting talk. So I have a question from Brian Schultz. He mentioned that this is a really cool experiment that fills an observational gap. So the question is, do you have a sense yet of what are your current observational gaps? Like, what are some of the things you like to see in higher resolution?
I can perhaps take this. I can see two things. There's certainly more. One thing is we need to understand why we have this stress heterogeneity, why the stress field seems to change across the fold. Is this because of slip has already occurred on this fold in the past? Is it because of material heterogeneities? And so what we're going to do is to do a lot of lab tests with the core material that we have. This is one aspect that we didn't foresee so much, but now we feel it's really important to actually do this lab test to understand the compliance contrasts or different elastic properties, how it changes spatially, and also how the strength changes. Another aspect that I'd like to highlight, I think what is a challenge is these on-fold observations. So to have fiber optics or other instruments across the fold that pick up co-seismic strain or the preparatory strain or these different effects, it's challenging because of, well, the fold is it's often flowing, and then you have to instrument a instrument across a flowing fold. it's doable technically, but it's challenges and it has stretches our budget a little, so to say. So I hope this
But
answers the question.
if we really manage to make a rupture through our arrays, then I think that one of the most spectacular observations that we could potentially make would be, high resolution temperature observations as the rupture approaches, and then maybe even ruptures through the fiber optics cable. And because we have real-time data transmission, we would, have that data up to the point where the cable may break, and that would be, a first observational constraint of actually how much heat is being produced on a fault zone during an ongoing rupture. And then, of course, there's a lot of precursory signals that we can potentially observe that we just may not observe often in more natural settings because we may not have the sensitivity and the resolution. If we can resolve it anywhere, we think we can resolve it here because of these very high sensitivity instruments.
Perfect. So the other question is from Sean Maxwell. He mentioned that interesting concept of trying to generate larger events as opposed to the normal strategy of reducing seismicity. So the question is, any insights into the main factors you have identified to increase seismicity magnitudes?
Yeah,
How
thanks
would
for
you
the
increase seismicity magnitude? Mhm.
Yeah, thanks for the question. I also think if we know how to enhance seismicity, we probably also know what not to do if you want to reduce seismicity. So I think the strategy also helps for the induced seismicity community in general. How do we manage this? So I think we have some hypotheses that are supported by data, and what we observe from all the deformation data is that actually far away from the injection where the pressure has already increased, we see a compression. And this compression may be if a rupture wants to run away and it meets this compressive zone, this sort of a compressive cage around the pressurized volume, it may want to arrest at this compression. So if we kind of erase this compressive cage by pumping up the volume and increase the pressurized volume before we rupture, then this rupture arrest may not happen there or may happen further outside. And this is something that we see happening in our deformation data. I didn't bring the figure, but this is something that supports our hypothesis that the preconditioning may actually work. But it also means if we would dare to generalize this, if we ramp up slowly the pressure steps or with a ramp, or we pump for a long time at lower pressure level, this is actually something that has the potential to enhance seismicity.
Mhm.
Not
And
Perfect.
sure
these
if
are
that
things that
answered the
we
question.
very intensely discuss at the moment because we're just starting to design the injection protocol for the large experiments. So I think uh, we yeah it's our own analysis in progress also.
Mhm.
Don't know final answers yet.
The next question is by Thomas Goebel. He raised his hand. Thomas, if you are available, please unmute yourself and ask.
Yes, hi. Hi, Men. Hi, Valentin. Great to see you.
Hi,
And
Thomas.
really fantastic talk. Very impressive what you guys are doing. Very exciting. Yeah, I was I understand the excitement about the magnitude 1 test, and there's no doubt about the importance and interest of the work. I'm just curious, any plans for the geothermal for the magnitude 0? And I'm kind of curious because it looked like you're activating two different volumes at different points in time in your injection history. And you may be able to resolve a little bit, right? What is causing the difference in seismic response? Is it, the way you inject, your preconditioning? Is it the pressure, the seasonal, or is it structurally controlled, right? Anyway, so the question, any plants, inject in summer versus winter, inject, closer or further away, in these different volumes that react differently seismically.
Hmm. Yeah, You touch on a very important point, and we have ongoing discussions on this for next spring or next summer. We need to decide upon an injection scheme, right? We need to think, do we do this preconditioning idea again? Do we engage with a different idea? And we're not sure. I cannot give you a definite answer, to be honest. And what I wanted to kind of point out in my part is how difficult it is to actually experimentally verify if one injection schedule produces a different outcome than the other. There's discussion on cyclic injections, on ramping up, on all when it comes to shut-in, on gentle shut-in or more abrupt shut-in and bleed off. So all these things. If you The problem is when you do go to the same volume, to the same interval, you always change the conditions a little bit. So repeating the two different injection protocols will lead to a different outcome anyway. Is it because one has been first and the other has been second? So injection history is relevant. If you do in different close by intervals, well, we're activating a different geological setting, and the geological setting has a big impact on the seismogenic response. So I don't know, to be rigorous, one would have to do, I don't know, 100 experiments in different locations, different places, one flavor and 100 the other way, and then we have a statistical data set. But I'm not sure. Perhaps I'm giving the question back to you. If you have an idea, if you have a recommendation, how we enhance our
Yeah.
seismicity.
No, it's no, I agree with what you're saying. Maybe there are some first order first order components that you could tackle first. Is it the case you made for seasonal pressure variation seemed to be quite strong. So maybe you could do something in that respect, right? Just when in the year you inject. The other question it looked like it was very hard to create this magnitude, minus 0.5. Was it a special asperity that fractured? So maybe you can drill into that volume and get some structural, without doing an additional stimulation, just understand a bit more, of that volume that was initially quiet, and then bam, all of a sudden you have this zero point 0.5 event. Could you track down, is it, you could do friction, look at the roughness of the fault. Is there something special about the zero point 0.5 patch? I don't know. Maybe we can chat more at a later stage, but it's a really cool observation. It's
I,
pretty impressive.
I think one can see from the seismicity pattern that the fracture that was reactivated turns around a little bit. So perhaps there has been a little change in orientation, hence a change in the slip tendency, which may have promoted this. But no, we cannot go and drill into this part here. That's not foreseen in this project, but we may do this in the geophysics, in the earthquake physics testbed in the future. Let's do first the experiment, see if we get some nice magnitudes, and perhaps in a future project, follow-up project, we may do this. It's a good idea.
It's in the at the earthquake physics testbed. This is easier because we, the new tunnel that we excavated allows us to get to the fault zone, with 50-meter long boreholes. At the geothermal testbed, this zone is about 120 meters down, and it's very difficult actually to even hit it with the borehole because we only have so much control on the borehole trajectory. And drilling is actually, so it's much easier to do additional stimulations than actually drill a borehole of that scale, and also cheaper. And maybe another comment is that we're really kind of running at the top of our capacity. We're trying to make all these exciting experiments happen, but it's a lot of work for a large team. But it's definitely a cool idea to drill into the zones that ruptures or that did not rupture. Yeah, so we're thinking about that.
Perfect. Thank you so much. We are on top of the hour for this webinar. Thank you so much, Men-Andrin and Valentin, for presenting for us. And I really appreciate having all of this discussion and question and answer. And the feedback that we receive from the audience shows that how important and interesting your topic is. Hopefully, we can have you in our future webinars as well. Thank you everyone for joining us in this webinar. The formal part of the webinar is over. But if Men-Andrin and Valentin are available, they can stay with us, and everyone who has other questions can ask the questions directly from them. Thank you.
Thank you very much for having us.
Yeah,
Sure.
thanks
Thank
for
you.
giving us the chance. Yeah.
Sure. Thank you. I have a question about one of your earlier slides. You mentioned that you need to increase the pressure to 20 megapascal for activation of the fault. So I was wondering if that is what you expected according to Moore Coulomb criterion. What did you expect as the increase of the pressure compared to 20 megapascal that you needed to inject for activation?
Yeah, based on the stress field estimates that we had at the time, it's kind of was not unexpected that it was at this 15 to 18 megapascal, somewhere where seismicity kicks in. So we had an estimate of sigma 3 being some 13 to 15 megapascal, and with a slip tendency, with a rough estimate of sigma 1 being the vertical stress and the orientation of the fracture, we came into this region. Yeah. But we knew the reactivation pressure, checking pressure from early experiments. We could benefit from all these past experiment sequences.
Mhm. So the fault is not favorably oriented then. It's not close to yeah, the strike is not close to SH max. For example, in normal faulting, a strike is not parallel to SH max.
Um,
So
no,
if
I don't think I would call this an optimally oriented fault. It's not a critically stressed fault in that sense either. And after all, we needed 15 megapascal to produce
yeah.
seismicity. That was kind of expected too. The region, although the Alps have some intermediate seismic hazard and there's a fair bit of seismicity there, this particular region is seismically relatively quiet.
Mhm. Awesome. So, as I'm not sure if you have done rock mechanic test for the for at least to obtain the friction coefficient of the gouge material. So maybe that would be a bit like a good extension of this work to have better estimate of what is required for the stress increase to reach to the failure criterion, to meet the failure
Yeah.
criterion for failure. Have you done any of those tests?
Yeah, we have done rock mechanics and frictional tests, and there's actually the Volpe et al. Paper from 2023 that I, as I was presenting, realized I should have put on my slides. And there's a lot of work that we haven't been able to summarize here. And I don't know the numbers by heart. The one of the key outcomes of the frictional test was that the gouge material itself is actually slightly rate strengthening. But it can be activated with enough fluid pressure.
Hmm. So what is the average friction coefficient for that? A static friction coefficient? Uh, like before start of the rate strengthening. Do you have any recollection of what was the initial friction coefficient before onset of reactivation or activation of the fault right at the onset?
I want to say
Um,
0.6, but I'm not sure. I need to look it up. It's a number.
Mhm.
Want to get right, I can get back to you on this.
Thank you. If there are other questions from the other audience, please unmute yourself and ask. we can run the meeting for another couple of minutes for you to ask questions directly.
Yeah, I don't know if you can hear me. It seems like my camera's not working. I'm sorry. So Pierre Fro, great talk. I mean, that's really exciting stuff that you're doing. You know, I was just curious, when you excavated these galleries and or drilled these wells, did you notice any activity, seismic activity, or any other deformation, in fact, induced by this drilling and excavation?
So we did pay attention. We looked very closely on the fault. We were hoping that we would see some activity on the main fault, but we didn't see much of that. What we did do is during the excavation, we built a sort of separate network around the to-be-drilled tunnel. This is called the pre-coat project, and it's summarized in the Hamdi et al. Paper that Valentin briefly showed with the stress model. And there, the purpose was to study the formation of the excavation damage zone with the soft excavation method instead of drill and blast. And so locally there were tons of seismicity just in the immediate surrounding of the tunnel, as expected, but on the 40-meter distant target fault, there was nothing
Okay.
substantial.
All right, cool. Thanks. Really cool.
Thank you.
Cheers.
So I remember another question, like in early slide you showed with the activation of the fault, the pressure, the flow rate basically dropped and the pressure increased. But with the activation of the fault, the compliance of the fault increases to receive more fluid, and the pressure drops and flow rate increases to compensate for that pressure drop. If you want to keep pressure at some maximum number, 20 megapascal. So why do we have the opposite trend in that earlier slide? Yeah, here.
Yeah, we were quite puzzled when we saw that. So for Valentin, maybe you want to comment on this. Is not what I would have expected.
I didn't follow exactly what is contrary to the expected
Yeah, so
expectations.
when the fault gets reactivated, there is some like gap for the fluid that you are injecting into the fault to receive that fluid. The pressure drops in that case, like because pump is at a specific flow rate, so it cannot accommodate that large volume that is generated by the reactivation of the fault. So the pressure in this case should drop, right? And the flow rate then needs to increase to keep the pressure constant. You know, pressure needs, like in this case, pressure drops.
Yeah, this is will be close to the source. We're still not sure 20 meters away from the source, and I think this is what we sort of managed to show with this stress interaction model. This very simple model is that we um, we may have this dilation at the source, but around you have the stress redistribution. There are
Uh-huh.
compressive regions, there are extension regions, and it so happens that we have extension, by the way, at the monitoring interval. So perhaps a little detail, but if you look at figure B and you follow the black line, there is actually a little pressure drop.
Oh, right. That is what I'm talking about. I was just looking
Yeah,
at black
so
line. Black
yeah,
line is far away from the
this
fault
is
plane.
right in the interval where we injected. And so we got a little volumetric expansion at
Yeah.
that location. But between the source and the interval where we injected, I believe that some flow paths have been obstructed a little bit. The transmissivity between the source and the injection interval has been compromised a little bit.
Mhm.
And that's why right at the interval, there has been an expansion, a little increase in transmissivity, but soon when we go into the rock mass, there is a transmissivity reduction. So
Mhm.
we have near wellbore effects that are contrary to the farther away, and farther away being meters to 10 meters away.
Mhm.
And so we just see the superposition of these effects. I guess with this one measure, the pressure is measured here at this stimulation interval, which is this where this red line is a bit thicker. And the main shock happened up here, and it's also laterally offset to I think about 25 meters.
Okay,
And
right.
another mechanism that could cause, so I intuitively also would have expected that the rupture would increase the transmissivity. But another, one thing that we actually see is that we may have opened the conduit to this structure above it, which then in the next experiment created all these blue dots up here that we weren't able to activate beforehand. And if you do that, and if you actually open up a conduit here and you allow material from here between where you make the pressure measurement and the main shock water to flow away, you could actually have poroelastic closing that would then make the integrated flow path less transmissive.
Exactly. Yeah.
But it's an interesting observation for sure.
Thank you. Yeah. Awesome. Any other questions, everyone? We have 6 people, three other people other than presenters and myself. I think the questions are over. Thank you so much again. Hopefully we can have you again later to have an update about this research in progress.
Yeah, in a year or two, we would have something more to report. Yeah.
Awesome. I look forward to that. Thank you so
Sure.
much, everyone. Have a great weekend.
You too.
Thank you too.
Thanks again.
Thank you.
Thanks a lot,
See you.
Tyrone.
Ciao, ciao.
Thank you.
Thanks you,
Bye.
Martin, for organizing.
Sure, definitely. Thank you.